recording now for Mackenzie to fill stuff in for her. And you guys can have access to this too, right? I'll put it there. Chapter 19 is electrochemistry. And in our lab presentations, there was a group from the other class that they presented something similar to this. They did electroplating. Y'all know how you would take something and maybe plate it with gold or silver or whatever. And so they did that, and I actually they took a nail, which nails are galvanized usually. Do you know what element they use to galvanize?
Gallium.
Oh, good guess, but it's not gallium. Gallium will turn into a liquid. Zinc. Things are galvanized with zinc. And so they took this nail, and to y'all it probably looks rusty on the end, but that's actually copper. They put it in a copper solution, applied an electric current, and made copper played out onto the galvanized nail. And that's electroplating. So what you do in electroplating is you use electricity to force a chemical reaction to happen that wouldn't normally happen. That's electroplating. In electrochemistry, you take reactions that want to happen and you generate electricity with them. Okay, and that's what I'm going to show y'all here on the cart in a little bit. Go ahead.
Is that the same thing that George used to do? They play
If they do like a grill on your teeth,
I've seen them drop it in this liquid and it'll start electricity and then it'll start turning gold. It's crazy.
what do they plate on something and then they put that something in the mouth, right?
Yeah, it's weird.
Yeah, I think I don't know how that process works all, but yeah, I'll bet you're exactly right. I'll bet it is some sort of electroplating with forcing it to plate out. So, guys, I need you to think back to Chem 1, to the coolest lab we did. What was the coolest lab we did?
One with the copper.
Yes!
That's when it grew, right?
Okay, it looked like
it grew.
it looked like it grew. We did a couple of labs where we used copper. Like if I showed y'all this bottle right here, y'all can see there's a blue solution in this bottle. Okay, I'm saying that for her benefit. Why is it blue? What makes solutions blue? Come on. Copper. Okay, so there's copper in this solution. And in y'all did 2 labs where you had a beaker with your blue solution. One time y'all measured out zinc and you put it in there. Another time y'all put a piece of aluminum wire in there. And that's what you're remembering, Zach, that it looked like the aluminum wire grew because reddish brown copper was plating out on it. And also, do y'all remember that at the end of that, there was no blue color in the solution? That's how you knew to quit that reaction. And when you pull that wire out, it was a lot smaller than when it started. Okay, so I'm going to do an example with copper and zinc. So what y'all had, like this blue solution, it has copper 2 ions in it. Okay, this is copper 2 sulfate in this bottle I'm holding. But I'm not writing the sulfate up here because it's a spectator ion. So I'm writing y'all the net ionic, really. So there's copper 2 ions here. And do y'all know that those are aqueous? Because it's a blue solution. And what y'all did in lab that day is you measured out zinc. It was a powdery gray zinc. And it was just a solid. And based on what I just told you, and I know I'm asking y'all to dig back to last semester, can you tell me what happened, what products were? Come on, I don't care if you're wrong as long as you're doing something.
Copper, zinc.
Okay. You ended up with this kind of copper, solid copper. It was reddish brown in lab. Y'all filtered it and you dried it and you weighed it. That's what you did, okay? In this example, you didn't recover the zinc, y'all. The zinc that you started with here, it actually disappeared like magic. Was it magic? No, it was science. Yes? Okay. This is a redox reaction. Remember the word redox? Redox is a combination of reduction, oxidation. Okay, I'm going to write something under this in a minute, so I'm going to go over here and talk about reduction, oxidation. In redox reactions, guys, electrons are transferred. Okay? Do y'all remember? I gave you a couple of acronyms, like oil, rig was one acronym. Y'all ever heard of Leo, GER? Okay, what do you remember about reduction and oxidation? Do you know what oil rig stands for? Oil. It's an acronym. Okay. Oxidation is the loss. Loss of what?
Electron.
Of electrons. What does rig stand? What's that an acronym for?
It's something that has to do with gain of
Reduction
electrons.
is the gain.
Reduction is the gain. And that's one acronym. Okay, the other one, Leo. Do you know what Leo says? Lose electrons, oxidize. Gain electrons, reduce. Okay. Y'all, what's the charge of an electron?
Negative.
Negative. So, like in oil or Leo, y'all, if you're losing electrons, if you're losing negatives, if an atom is losing negatives, what's that going to do to its oxidation number?
It's gotta go up.
It's going to go up, right? And if in reduction, that's where the electrons are going. It's gaining the electrons. So what's going to happen to its oxidation number? It's going to get smaller. It's going to decrease. Okay? So, knowing that, and a reminder of reduction and oxidation, what here is being oxidized? The zinc is being oxidized. And we use the term oxidation in everyday life. Corrosion is oxidation. And, you know, when we say something corrodes, or maybe you say it oxidized, y'all, it's being eaten away. For battery terminals, whether it's like a shovel in the yard or something metal, it's being eaten away, it's getting brittle.
Is that just because like it's a solid on this side and it's aqueous?
No,
on the
it's
other?
not because it's a solid, it's an aqueous. It's because, what is the oxidation number for this zinc right here? This zinc here has a 0 oxidation number. This is a Chem 1 thing. How do you know it's 0?
What are the middle ones, right?
It's a transition metal, but
Right, yeah.
what'd you say? It's an element. Anything in its elemental form has a 0 oxidation number. What's the oxidation number for this zinc? +2. Okay? So in this reaction, zinc went from 0 to +2. It was oxidized. It had to lose electrons for that to happen. Okay? Copper. What's the oxidation number on the reactant side for the copper? +2. What's the oxidation number on the product side for the copper? 0. So we know that the copper was reduced. So when you have oxidation, when you have electrons being transferred, guys, you always have something being oxidized and something else being reduced. They can't both be oxidized because they've got to go somewhere, they being the electrons. Now, whatever is reduced is referred to as the oxidizing agent. And whatever is oxidized is referred to as the reducing agent. And I think of it as the agent is something that helps something happen. It's the agent, it's the helper. And okay, of acid and base conjugates, yeah. So the reducing agent is oxidized. That means when it loses electrons, it's giving them to what's getting reduced. That's how it's helping something get reduced. So, what we can do with this reaction and the purpose of electrochemistry, y'all, this reaction in Chem 1, this happened in one beaker, okay? The idea behind electrochemistry is if we take these things and we put them apart in different beakers, and we connect them with a wire, we can make the electrons flow through the wire and we can generate a voltage. Okay, and that's what we're going to do. So first I want to show you how to split these reactions up into what are called half reactions. So if I were to split them up into half reactions, then what I would have is copper, 2 ions making solid copper. That's one half reaction. The other half reaction, I take the zinc, going to the zinc 2 ions. Okay? Just what I did, splitting it. I mean, you've never done it before, but does that make sense? You take whatever's being oxidized and you write that happening. And you take whatever's being reduced and you show that happening. Now, when you split things into half reactions, they have to be balanced. They have to be balanced in terms of atoms, just like you balance equation. Y'all, these are balanced, right? Copper and copper, zinc and zinc. When you do half reactions, you also have to balance them in terms of charges. So, look at the copper one. Right now, what's the charge on the reactant side? Plus 2. What's the charge on the product side? 0. We've got to make that balance, and we're going to balance it with electrons. So where do I need to put electrons?
On the products.
Don't I need to put them here on the reactant side? Because if I put 2 electrons there, that's 2 negatives. This is 2 positives. Now this has a 0 charge. And now the charges on each side are balanced.
So you always want to make them the smallest? You don't ever want to.
Well, the electrons are negative. So yes, you're always going to balance going to the smallest charge. Okay? Now look at the bottom one, the zinc one. What's the charge on this side? 0. What's the charge on the other side? Plus 2. What do I need to do? I need to add 2 electrons to the product side. Okay? So, let's say a little bit about this, because the more you do, you'll see this happening. But guys, when you're doing a redox reaction, whatever's getting reduced, the copper, it's gaining electrons. Electrons are always going to be on the reactant side. Whatever's getting oxidized, the zinc, whatever's getting oxidized is losing electrons. The electrons are always going to be shown on the product side. When you balance the half reactions, you will always have to balance them by putting electrons on the opposite side of each one. You'll never balance it and have electrons on the reactant of both sides. That says, oh, you've done something wrong. Okay, it's always going to be like this. Also, you can tell that when you add these 2 together, they just are going to go back to what I have up here. Right? Because the electrons cancel out. The number of electrons, 2 electrons, has to match. Okay? So let me show you what would happen, say, if you had this half reaction. And this half reaction, because this is actually the one y'all did in Chem 1 where you put the wire in there. It was aluminum wire, and you pulled it out, and it was all corroded. Where do I need to put electrons on the top one?
On the reaction side.
I need to put 2 electrons on the reactant side. Where do I need to put electrons on the bottom one?
On the product side.
How many do I need to put? 3. Okay? 2 and 3 don't balance out. So what you have to do is you have to multiply both the equations by some number so that they'll balance out. So do you guys see that you'd have to multiply the top equation by 3 and the bottom equation by 2? So that's a total of 6 electrons. That's how you figure out how many electrons are we talking about transferring. Okay? Now, I'm going to say this again in a moment, but these processes, these are intensive properties. Do you remember what an intensive property is versus an extensive?
And there's something with the interior of the.
Okay, it depends only on itself, so it's kind of like, yeah, the interior. Y'all, extensive properties dependent on amount, like mass. The mass is something depends on how much you have. That's an extensive property, okay? Intensive properties do not depend on amount, like boiling point. At what temperature does water boil? 100 degrees Celsius. Does it depend on how much water you have? No, water boils at 100 degrees Celsius. That's an intensive property. What we're dealing with here, these are intensive properties. So in doing this, we have changed it to be 6 electrons, but in multiplying these equations, we have not affected the voltage. Okay? And you're going to see that shortly. So, how do I separate these processes into a half reaction to create a battery, to generate a voltage? It's going to look something like this. Oops, wrong thing. I pulled a picture earlier.
It's kind of reminds me of Breaking Bad when they're
Yes,
in the desert.
I used to actually, Breaking Bad, yeah, you've seen it obviously. No?
Yesterday.
Did you? Okay, sometimes I used to start this lecture by showing the clip of one of the early episodes when, have you seen it?
They're in the RV and they get trapped.
Where they're in the RV and Jesse leaves the keys in the RV and it's dead. They're out in the desert and the battery's dead in the RV. Okay, and then Walt, right? He's a chemistry person. He's a PhD in chemistry, and of course they've been in the desert doing nothing good. Battery's dead. Cell phones don't work. And what Walt does, if y'all remember, he gets galvanized items from the RV, galvanized as zinc. Okay, this picture is not showing zinc. It uses copper as that part. And he gets copper. Okay, this picture is a little different than that. And he makes a battery to jump off the... Yeah, I used to show that clip because it's really funny.
I had a question about how many pores of red phosphorus in the water.
Yeah?
Is that true that it makes phosphine gas like that?
Yes.
Like quick?
Yes.
That's crazy.
Yeah.
Was it? They kept turning something for so long. You remember that before he actually experimented with this one? That's been a while since I've seen it. But he was sitting there turning something. They would take turns turning something.
Weren't they trying to crank
Trying
the
to-
generator?
Yeah, trying to get a spark. Basically.
Yeah, I don't remember that, but they did. Ultimately, what Walt did was the copper zinc thing, which I'm going to show y'all in a minute, okay? But let me tell you how we do it. You take a solution. At the anode, y'all, oxidation happens at the anode, okay? Keep that straight. They're both vowels. Oxidation, anode. They both start with a vowel, okay? Oxidation happens at the anode. What happens at the cathode? Reduction. Okay, how do you know what the anode and the cathode are? And that's where you guys are going to use your handout that you have in front of you. Mackenzie doesn't have one. The handout is page 887 in the book. So I'm saying that for her. When she watches this, she can look at it. Okay? The handout of your standard reduction potentials. So in the example here, y'all, do you see that I have, this is a piece of copper, copper 2. And on the right side, I have a piece of silver in Ag+1. So go on your sheet. Mine's written on, hang on. Find the copper and the copper plus 2. That's right here.
Silver's above copper, like 7 up.
I think that's the... Okay, do y'all see them? Okay, so you,
At first I was like, aren't they alphabetical? And I was like,
they're
oh,
not alphabetical.
this E thing.
They are in order of their standard reduction potentials, okay?
There's also a Cu2 plus 2 E negative.
You know what? I circled the wrong copper one.
You see what I'm talking about? It's right above
Yeah.
it.
That's,
There's a second copper one, like
It's the
three,
same thing that-
four, then
This
three
is what I
down
want.
from the other one.
this is the one I want. Do you see? It's the copper, it's the one that's 0.34. And the silver one, I actually kind of circled two numbers. Well, shucks. Okay, here's how the table of standard reduction potential works. Y'all can see on the left and right side, there's little arrows. Like right here, there's an arrow pointing up on the right side. And it's kind of hard to read, guys, because of the photocopy. But see it says increasing strength as an oxidizing agent? Do y'all see where it says that? Okay, so that means the stuff that's showing up on the left side of these reactions, those are oxidizing agents. Those are what's going to get reduced. And then on the right-hand side of the sheet, there's an arrow pointing down, and it says increasing strength as a reducing agent. That means the further down you go, you're looking at something that's going to be oxidized on the product side of this reaction. Okay? This sheet you're looking at, what's the title of it? Standard reduction potentials. This only shows reduction potentials. Okay? Is everything getting reduced? No. The cathode is the reduction. The anode is the oxidation. Yes? How do you know what's the cathode and the anode? It's where they are with respect to one another on the sheet. The cathode is always higher up than the anode.
Or silver, the copper.
Yes, hence silver is going to be our cathode, right? And if you look at my picture, silver's the cathode. Copper is going to be the anode because it's under it. And if you look at the picture, copper is the anode. Okay, and that's what y'all are going to have to figure that out in a minute when I go to hook these up, and you're going to have to tell me what's cathode, what's the anode. Okay, so what you do is you take a copper electrode here, put it in a copper solution. You take a silver electrode, put it in a silver solution. Connect them with a wire, a voltmeter, so you can measure the volts. Okay, electrons are going to flow. It doesn't show it on this. But electrons are going to flow through the wire in this direction. Okay? They're moving like so. They flow from the anode to the cathode. And that makes sense because what's the charge of a cathode?
Positive.
Positive. And so electrons are wanting to go to the positive cathode. So what happens as this anode, in this example copper, y'all, as it loses electrons, losing electrons is oxidation. That means this electrode here is going to start getting smaller. It's going to start losing mass. Because see, this piece of copper here is solid copper. As it loses electrons, it's going to be being eaten, and copper 2 ions are going to flow into this solution. Okay? As the electrons flow over here toward the silver cathode, what's going to happen is these silver ions in solution, they're going to grab those electrons, they're going to get reduced, and they're going to start to make this silver cathode increase in mass. It's going to get bigger because they're getting reduced, and they're kind of plating out on it, if you will. Now, what will happen as the electrons flow, as you have an influx of cations into this solution, and you have these cations leaving and plating on the silver electrode, you get a big imbalance in charge between the two. And that imbalance can get so big that the electrons will quit flowing. So what we do is we add something called a salt bridge that's shown here. Your salt bridge needs to be some kind of chemical that won't react, okay, with what's in either compartment. So how do you pick that? Well, it's kind of based on our solubility rules from Chem 1. If you'll recall, that group 1, those things are always aqueous. Any compound formed from a group 1 metal is aqueous. So see, that's a good metal, like sodium something. You might also remember in solubility rules that nitrate ions are always aqueous, right? So sodium nitrate in this example, and the one I'm going to do today on the cart, I'm using potassium nitrate is my salt bridge. And so what the salt bridge does is, as you start flooding this thing right here with excess copper 2 and the positive charge starts building up, the nitrates, the anions from the salt flood into here to balance that buildup of plus charge, okay? As you lose your silvers here, the sodiums replenish those positive charges that are being lost.
So basically, that salt bridge is bringing everything back to the
It's keeping the charges balanced. It's equalizing the charges, keeping the battery working. Okay, now, there's a number on this, 0.46. That is called, this 0.46 is called things like cell potential. That's one term for it. But with some other terms. Cell potential, cell voltage. I just don't, if it's ever presented in a different vocabulary, I don't want y'all to say, what is that? Okay, this is what it is. It can be called cell electromotive force or cell EMF, electromotive force. Cell. Yes. This is a cell. This copper is 1/2 cell. This silver is another half cell. That's not like biological cells. So that's where that's coming from. Okay? I usually say cell potential. That's my vocab. Okay? But I'm not sure how it's going to be presented to you guys on Connect. I think it'll say cell potential. So how do you calculate the cell potential? Well, there's a nifty little formula. This stands for cell potential. Hmm?
That what this is?
Yes. You simply take the potential at the cathode minus the cell potential at the anode. Okay? Another way to express that, because what happens at the cathode? Reduction. So another way you can sometimes see that is you take the reduction potential minus what happens at the anode,
Oxidation.
the oxidation potential. So sometimes it's presented as cathode minus anode, sometimes it's the reduction minus the oxidation. Okay? So now go back to your sheet. Let's find the cathode cell potential. We've already circled it, right? The cathode cell potential for the silver is 0.80 volts. Minus, what's the cell potential for the anode? 0.34 volts. Okay, now let me say, what's the potential then? .46 volts. Yeah? Okay, look what the number is on the voltmeter. Voila! 0.46 volts. That's how that was arrived at. Okay? Now, let me go back and remind y'all what I was saying about intensive properties. Okay? On the left side of this, the anode, copper is being oxidized. So what's happening over here is this, isn't it? Copper being oxidized. What's happening on the right-hand side? Opposite for silver.
Reduced.
Yes, silver is being reduced. Okay? When you look at your table, do you see that the silver this is a table of reduction potentials. So what's written for the silver is what's really happening. But what's written for the copper, the reverse of this is happening. But do you see that? That doesn't mean when we calculate the answer that we flip the sign of it. Right? We simply take the number straight off of this table. Even though it's the reverse of that process. It will always be, when you find them with proximity to one another, the top one is written as it's happening. The bottom one, the reverse process is what's happening. Okay?
Is that why it's minus and then it's 1 more?
Probably so. Yes. Yeah, that's exactly why it is, because it's taken into account the formula. Good spot on that. Okay? Also, Look at the silver and the copper one. Y'all, it's already balanced for charges for you. We looked at how to do it ourselves earlier. But do you guys see the silver's got one electron, right? And the copper had to be balanced with 2 electrons. If we were to add these two together, we talked earlier, you got to make the electrons equal, right?
Multiply the top
That,
one
that
by
means
2.
you have to multiply the top one by 2. So that means really we're talking about 2 electrons being transferred. But y'all, it's an intensive property. When you multiply the top one by 2, do you double the voltage? No. It's still 0.8 because it's an intensive property. The more water you have, it doesn't mean you're raising the boiling point. It's an intensive property, does not depend on amount. Okay?
So no matter how much silver copper you have, it's going to still be 0.46.
Yes. Okay, no matter how much, what Josh said is no matter how much silver copper you have, it would still be 0.46. Yes and no. Okay? Look on this formula. What does this little degree symbol mean? Standard. So, these are implying 1 molar concentrations. Okay? What I'm giving you, we're doing 1 molar. Your homework is 1 molar. We are not looking at concentration gradients, but Josh, you can change the concentration and adjust things. Okay? Now, I want to show y'all these on the cart, but I'm not going to be able to record that, obviously. But then there's one more thing I want to tell y'all because I know there's a connect problem that does this for chapter 19. So I'm going to hang off on that and go ahead and finish this so the whole lecture's together. You can connect cell potential to Gibbs free energy. Oh, how wonderful. And so there's this, what's the symbol for Gibbs free energy? Delta G. Delta G standard is equal to negative N F E. Okay? N like a who? Lowercase n, not a cursive one. Okay? What is N? Remember PV equals nRT? Moles. Okay? In this problem, the N, it's the moles of electrons. That's why I've been showing y'all how to balance the electrons, right? It's like a 1 or a 2 or a 3 or a 6 or whatever. It's the moles of electrons. Okay? F is a constant, and it's called Faraday's constant. And I would give this to you on the test. You don't have to memorize it. Faraday's constant is 96,500 joules coulomb per mole of electron. That's the units.
Say that again, Cooper or what?
Coulomb is a unit of charge. This is Coulomb. Coulomb. That's Coulomb. And that's the unit for electrical charge. Maybe y'all saw that in physics too?
I didn't say it.
Y'all didn't do physics too?
I've seen it
It's
before.
coming.
No, no, not
Okay.
I've seen it before.
You've seen it before. Okay. Coulomb. That is the same as 96,500 joules per volts times moles of electrons. Okay? Same number, but you can express it in terms of different units. What is E cell?
So the volt,
Volts times mole of electrons. Okay? What's E cell? Cell potential. Cathode minus the anode that you just did. So you can calculate the delta G. What you're going to want to watch for, if you do this on Connect, watch your units, because y'all, this constant is in terms of joules, and most of the time delta G's are reported in terms of kilojoules. Okay? So, how many, 96,500 joules, how many kilojoules would that be? 96.5. Okay, so just watch units, and we've practiced that on watching units, okay? But it's just a formula, and it's just plugging stuff in. Now, that's that.